Alrighty. Hi, everyone. Happy Fossil Friday. We are back with another Fossil Friday web chat. I'm Brittany Stoneberg. I'm the Outreach and Communications Coordinator for the Western Science Center. We have Gabriel Santos here with us as well.
Hi, everyone. Happy Fossil Friday.
I can hear my own iPad. Technical difficulties. Gabriel Santos, who is our Outreach and Communications Coordinator for the Raymond M. Alf Museum. And today we are talking with Randy Flores. He is a researcher and lab assistant working at the University of California, Los Angeles. His work involves studying the chemistry of fossils to learn about animals and climate conditions of the past. He is also, and I think Gabe will be really excited about this, a huge Star Wars fan and a musician in his free time. So I'm sure you two will have lots to talk about. Well, thank you for joining us today, Randy.
Well, thank you for having me. I'm really excited to be here.
Awesome. Yeah, so we're very interested to hearing about what you'll be speaking with us today.
Should be fun.
Great.
Absolutely. But it's not about Star Wars, it is about fossils.
Oh, man.
Sorry.
That's okay. I'll deal.
Yeah.
All right, Randy, whenever you are ready, take it away.
Sure. Yeah, I'll go ahead and set up my share screen.
Mm-hmm.
Okay. All right. Just 1 second. I'm trying to get my slideshow set up here. Okay. All right, and hopefully everyone can still hear me. We're just going to go ahead and launch into today's talk, which is titled Megatooth Mysteries. So we're going to be talking about some very special fossils. But not only that, we're going to be delving a little bit more into the side of chemical analysis of fossils and how we can learn things about fossils from understanding their chemistry, which is a bit more of what I do. Before we get into that, Brittany just went ahead and did an introduction for me, but just to expand on myself just a little bit more. As she mentioned, I am a researcher and lab assistant working at UCLA. And I graduated from UCLA as an undergrad in 2018. But prior to attending UCLA, I attended Pasadena City College. I was very fortunate to be able to spend time at PCC. I had a really great experience there, and I feel like it definitely contributed a lot to my academic path. I was just able to meet some great professors and really hone in on what I wanted to do. I don't know if anyone listening is maybe thinking about attending community. The first academic experience I would recommend it to anyone who's considering it. It just gave me a lot of opportunities to figure out what I wanted to do and get really excited about geology, the field that I ultimately ended up in. So just some photos here of myself. On the top left there is a trip that I took with Pasadena City College. I think that was taken in Utah. We were out collecting fossils for a field trip. We were specifically looking for trilobites. So one of the things that got me really excited about geology in the first place was having this opportunity to go out into the field and learn about these rocks and fossils that I had studied since I was a kid, and then actually be able to apply that into an academic path. To the right of that is a photo more recent. That's me working in the lab where I am currently. So as I mentioned a little bit, I now work more on the chemical side of things, or the geochemical side of things, rather than the strictly paleontological side of things. That's definitely still where my passion lies. And so, as you'll see in the talk today, wherever I can, I try to get involved in research that lets me deal with fossils and think about ancient life and all those sort of related things. And then more personal photos there down at the bottom. To the left, playing music with my dad, something that's always been really important to me. And then to the right there, as we spoke about, a very big fan of Star Wars, desperately waiting an opportunity to get back to Galaxy's Edge. So, with all that out of the way, we can jump into the subject of today's talk, the Megalodon shark. The Megalodon is one of the iconic examples of ancient life. I think many people would be familiar with its role in pop culture, especially recently. But the Megalodon was exceptional in that it was really a gigantic shark from a China geologic record called the Miocene through the Pliocene. So from approximately 23 million years ago to somewhere around 2.5 million years ago, probably at the most recent. And the exact specifics of its time of extinction are something that's still debated, and maybe a topic that we'll kind of touch on later in today's talk. But the thing that really makes it stand out, as I mentioned, was its size. The Megalodon may have grown up to nearly 20 meters long, weighing upwards of 20,000 kilograms. So really, really just an impressive animal. And you can see to the right there that picture of the tooth where the Megalodon gets its name, literally the megatooth, was a sample that I was fortunate enough to be able to interact with thanks to Kate Santos, actually, there at the Alf Museum. So our estimates of the Megalodon size are based on these teeth. Really, that's just about all we have to work with in terms of being able to reconstruct what this animal looked like and how it lived, are just based on these giant teeth that it left littered around the world after it went extinct. So if we want to go a little deeper into the mystery, one of the things that is continuously or has been debated about the Megalodon was the specifics of its physiology. So whether it demonstrated some kind of endothermy or whether it was warm-blooded or cold-blooded. Pictured there are two relatives of the Megalodon shark in the order Lamniformes. So these are the sand tiger shark and the great white. The sand tiger shark being a classic ectotherm in that it doesn't regulate its own body temperature, whereas the white shark has the ability to maintain an elevated body temperature relative to the water around it. So something like 10 to 15 degrees Celsius higher than the water around it. So that's one important question that we want to be able to better understand about the Megalodon, was whether it was something like a classic interpretation of cold-blooded animal, something more like the white shark, or something else entirely, something even closer to a conventional endotherm, like even like a whale or some other kind of marine mammal. And once we have a better understanding of that, we want to be able to understand how the physiology may have contributed to its life and ultimately maybe to its extinction. As we better understand the Megalodon, we would like to know how its lifestyle may have contributed to it going extinct after being a dominant apex predator for tens of millions of years. And so lastly, in order to start to unravel this mystery, we want to know what the isotopes in the Megalodon teeth can tell us. As I mentioned, we'll be diving into the chemical side of things. So before we can do that, we would like to make sure that we're all on the same page, just in terms of knowing what we're talking about when we reference isotopes. So just the basic background. Matter is made of atoms, which comprise elements from the periodic table. So we just have a very simplified cartoon here of a carbon atom just showing the protons and neutrons in the nucleus of the atom. So what we're seeing here is what identifies the carbon being those 6 protons, which make it a carbon. That's what identifies it as that element and makes it have those chemical properties. But we can actually have a variation in the number of neutrons in the nucleus that will ultimately change the mass. There you can see we have a total mass of 12 and a total mass of 13. And those additional neutrons don't change the chemical characteristics of the atom. That's all just dependent on the number of protons. But when we talk about isotopes, what we're talking about is this variety of different total masses depending on the number of neutrons that we have in the nucleus. And this difference in mass really is what provides the basis of the field that I work in, which is stable isotope geochemistry. So these differences in mass will affect, can be influenced by the environment that materials containing these elements form in. So diving just a bit deeper into our background in isotopes, the the type of isotopes that I study specifically are known as clumped isotopes. And clumped isotopes are referring to a molecule containing 2 or more heavy isotopes bonded together. So again, just a crude example here of a carbon dioxide molecule, which is the clumped isotope molecule that we look at in my lab. So if you can see there, we have an oxygen with mass of 16, so we would refer to that as a light isotope. Then we have our carbon with a mass of 13, so that being the heavy isotope of carbon, bonded with a heavy isotope of oxygen. So that bond right there between the carbon and the oxygen, those 2 heavy atoms, is what we refer to as, what makes this a clumped isotope. The special thing about these is that clumpiness of isotopes found in a mineral sample, or specifically in this case, a biomineral, that being the minerals that make up the teeth of the Megalodon. The formation of those clumps is a process that is dependent on the temperature from the environment where the mineral formed. The specific mechanics of this are rooted in thermodynamics. So something that's definitely a bit beyond the scope of what we'll be talking about today, but suffice to say, this formation of clumpiness in molecules is dependent on temperature. So you can imagine that if we can analyze these, this can be a powerful tool. And the case is that this temperature dependence allows us to use clumped isotopes as what's called a paleothermometer, which is just exactly what it sounds like, a thermometer for something ancient. We would also refer to something like this as a proxy, which is basically a way of indirectly measuring a value that we can't measure directly. If we want to know about the temperature of a shark tooth from a shark that lived 10 million years ago, obviously there's no way for us to measure that directly. We would need to use something that we refer to as a proxy to be able to get that value. So that brings us to talking about how we actually measure isotopes, or our clumped isotopes in our lab. And so just kind of a brief overview to show you the machines that we work with in our lab. We have one example here on the left, the machine that we refer to as the Sarlacc. So this is where the sample actually gets digested. If you're familiar with the Star Wars lore, you may recognize the name of the Sarlacc as the beast that digests its victims over 1,000 years. And so the aptly named Sarlacc is where our sample powder gets digested. We produce carbon dioxide gas that we talked about earlier. And that's how we measure our clumped isotope molecules. To the right, there is a picture of the actual mass spectrometer itself, which is the part of the apparatus that actually measures the sample and gives us our isotope values. One just important thing to mention is that the field of clumped isotopes is actually still relatively new, having been around for maybe the past 15 years or so. And it's only been fairly recently that we've actually had the precision on these instruments to actually accurately measure these values because they're so small. Okay, so now that we have an idea of clumped isotopes and how they work, we can start thinking about some of the applications that they have been used for in the past that would be relevant to the mystery that we have on our hand regarding the Megalodon. And that involves these 2 animals here, specifically the Camarasaurus, which is a sauropod dinosaur, and the Oviraptor, which is a theropod dinosaur. And the researchers who investigated these questions really had some of the same questions that we're talking about right now, which is, what is the physiology of these animals? There's been a long-standing debate in regard to non-avian dinosaurs of whether they exhibited the kind of classic cold-blooded lumbering beasts of old, or whether they reflect the more modern interpretation that we now see of very active, warm-blooded, and bird-like animals that we know them to be. So in order to get to the bottom of that mystery, they took the approach of investigating the teeth of the Camarasaurus. So you can see a little inset there showing a close-up of what those could look like. And now these teeth are made of a mineral called apatite, specifically bioapatite in the case of these coming from a living animal. That apatite contains material that we can analyze for clumped isotopes. And in this case, these yielded a result that showed that the Camarasaurus may have exhibited body temperatures on the order of 36 to 38 degrees Celsius. So something really comparable basically to a modern mammal, much more warm-blooded than maybe the classic interpretation of this dinosaur. In the case of the Oviraptor, and rather than looking at the teeth, they were actually able to look at eggshells. These are made of a mineral called calcite. But the same idea applies in that these have material in them which we can analyze to investigate clumped isotopes. So the eggshell was formed inside of the dinosaur. The shell mineral precipitated from a fluid that theoretically reflects the body temperature of the interior of that dinosaur. So by investigating the composition of the shell, we're able to figure out the body temperature of the animal that it grew from. So just a couple of things that really get me excited about the field of clumped isotopes. I wanted to share these examples. So now that we have an idea of things that we can use clumped isotopes for, have an idea of how they work, we can get back into thinking about our first question, which is how can we apply this to the Megalodon? So in order to start thinking about that, the last thing that we need to do is actually deciding how we're going to define this relationship between this clumpiness that we see in isotopes in the teeth of the Megalodon and the temperature that they grew at. So I mentioned before that isotopic clumping is dependent on temperature. So we know that this relationship exists, but in order to actually take a measurement of clumped isotopes and extrapolate that into a temperature, we need to actually define the relationship between those two things. So to do that, we can plot these two values against each other on a plot like this, just like on an XY plot. So the value there on the y-axis on the left indicates the clumpiness. So that's a little triangle shape with 47. So that's basically just telling you something about the abundance of those mass 47 molecules that we mentioned. So that's the amount of clumping that you're seeing in that sample. And as it turns out, you can see that as you go higher over here on this scale, more clumping that relates to a colder growth temperature. We'll see that in just a second, sorry. So in order to define this relationship, we want to take modern samples and apply those here so that we can better understand how to make that understanding of our past samples. So we can take a modern sample of something like a sand tiger shark that was grown in an aquarium at a temperature that we know. So the teeth of this shark should reflect that water temperature. So say if this was grown in an aquarium that was held at a constant 25 degrees Celsius, the teeth of that animal grew in that water temperature. And so the clumped isotope signature should reflect that water temperature. And so we can see that over here, coming in at around 25 degrees Celsius and its corresponding delta 47 value. And so we have 1 point here on the graph. And then next, we would want to add in another point. So we could take something like a Greenland shark, so something that grows in much colder water temperatures on the order of 1 to 2 degrees Celsius. And so now we have 2 points on this graph defining a relationship. And as I began to allude to, you can see that a higher degree of clumping occurs in these colder samples relative to something that grew in a warmer temperature, which has a lower degree of clumping. So now we have 2 points on a plot, and what we can do next is define a line between them. And I'm aware of the fact that it looks like the sand tiger shark is attacking the Greenland shark with some type of heat vision. That was an unfortunate artifact of drawing the line between these two, or maybe a fortunate artifact. It does look pretty cool. But once we have that line, we have the equation of the line in the format of y equals mx plus b, where in this case, the y value corresponds to the 47 value, or the degree of clumpiness. The x corresponds to the temperature that the teeth of the animal grew at. And if we substitute those values in, now we have an equation that we can use to identify sample unknown. So we can take a measured delta 47 of our fossil megalodon tooth, and then just doing some algebra to rearrange this, we can identify our growth temperature of the tooth, which is our sample unknown. And that's what we really want to get to at the end of the day, is to be able to identify the temperature that these teeth grew at, with the theory that rather than reflecting the temperature of the water of an ectothermic animal, the teeth will reflect the temperature of the body fluid that they precipitated from, just the same as it did with the oviraptor and with the Camarasaurus. So with that understanding in mind, we can start to think about where the Megalodon would fit on this type of scale. So that brings us to the preparation here of our samples. So What we're seeing on the left there is a student by the name of Allison Newman. So she's one of the students that worked on actually prepping these tooth samples by drilling them with a micro drill. So literally she's just taking a very fine drill and powdering some of the sample so that we can run it through our machine. As you can imagine, this is a very time-intensive process. Thankfully, the teeth, they're so big that it doesn't take multiple teeth to sample. Even just out of one megalodon tooth can give us enough sample for several replicate analyses, whereas some of the smaller teeth, like the moderate teeth, looked at, like say for example, a sand tiger shark, it would take numerous teeth, which would just take even longer to analyze. We have a picture of a scanned tooth cross section. The idea of just the composition of the teeth. 2 weeks ago, there was a talk entitled aptly Tails Teeth Tell, and if you're interested in learning more about the morphology of teeth, I would highly recommend checking that out. Tara did an excellent job of diving into the function of teeth and the different components of them. But for the purposes of what we're talking about here, I just wanted to point out these two different components of the shark tooth that we think about when we're prepping our samples, which are this outer sheath of material known as amyloid, which you can kind of see as that lighter white material, as opposed to the kind of more spongy looking dentin on the inside. And again, these are both composed of bioapatite, same as they were with the Camarasaur tooth. But there is potentially a difference in the isotopic signature that we might see between these two different parts of the tooth. So when prepping them, it is important that we distinguish them. So that provides just another challenge to Allison and the other students working on prepping these samples, and that they have to drill very carefully just to make sure that they're getting either only that outer sheath or the interior portion of the tooth so that we can keep them separate when we do our analysis. So after thinking about our clumped isotopes, getting a rough idea of how they work, some of the things that they've been applied to in the past, and then ways that we can define a relationship between tooth growth temperature and clumped isotope signature, we can now get to some of our preliminary results of this investigation. So some of our preliminary results suggest that the megalodon body temperatures may have reached as high as 35 to 40 degrees Celsius, which is really impressive and exciting. This is, again, preliminary data, so this is coming from a handful of analyses, but it can be really exciting because it suggests that the megalodon may have been quite warm-blooded, something like close to the body temperature of like a modern whale. And so we can follow that conclusion to our second question, was whether this had something to do with megalodon being driven to extinction. So maintaining this body temperature would have required a high degree of food intake. And if that was the case, changes in environment that may have contributed to food scarcity, increased competition with other marine predators, such as like predatory whales or like the great white shark that were evolving around the time that the megalodon went extinct. All of these factors could have potentially played into the extinction of the megalodon, now that we have an idea that potentially this high demand for food was going on for them in order to maintain this high metabolic rate. So by getting a better understanding of the physiology of megalodon, by looking at its teeth and the chemical composition of them, control some potential drivers for extinction out. Like under the assumption that megalodon was cold-blooded, some folks have proposed that in changing climate, it may have been restricted to certain areas of the ocean where it didn't have access to food. But if it is the case that it was warm-blooded, as what we're suggesting here, or endothermic, that wouldn't have been such a concern because it would have been able to have a more global distribution. So then we have to start thinking about some other factors that may have contributed to its extinction. So we kind of close some doors and then open some more for additional questions, which brings us to our last point. As is often the case with the scientific process, there's always more work to be done. We plan on doing additional analyses of modern shark teeth to really fill out that calibration that we were talking about earlier and defining the relationship between growth temperature, shark teeth, and clumped isotope signature. And we also plan on doing additional analyses of the Megalodon teeth themselves and maybe some contemporaneous fossil teeth to also kind of act as a frame of reference for the results we're getting for the Megalodon. But that brings us to our conclusion for now. So thank you so much for listening. Just wanted to include some names as thanks for folks who have made this project possible. And of course, thank you so much to Brittany for hosting this meeting, and thank you everyone for tuning in. And I hope that everyone enjoyed the talk and was able to learn something.
Awesome. Well, thank you for sharing that, Randy.
Well, thank you for having me.
Yeah, that was really cool. That's a lot of stuff that I had no idea about.
Same. It's not my strong point when it comes to paleontology, so it was very interesting reading about all this.
Yeah, well, I hope it wasn't overbearing. I know that, yeah, the chemical side of things tends to maybe not be so exciting, but lots to learn from it. So I again, thank you everyone for tuning in. And
Of course. And before I let you and Gabe devolve into Star Wars chatting, if anybody in the chat has any questions that they'd like to ask Randy before we finish up today's talk, feel free to put them in the chat and I will pass them along. Don't have any questions quite yet, but if anybody does, I will let you know.
I have a question. So,
sure.
When people think about paleontology, a lot of times they just think about it's looking at bones, but your research project is a whole different kind of field of paleontology where you're taking chemistry and geology. Is that something you thought you'd find yourself doing when you wanted to go into this kind of career?
No, yeah, like when I first started thinking about doing geology, I never even considered like the chemistry side of it. I really just wanted like, and it wasn't until I think when I got to UCLA and we learned about our paleoclimate lab, and I actually started doing work first with forams. If anyone doesn't know, foraminifera are microscopic organisms that live in the ocean that are commonly used in studies for figuring out past climates. They're kind of like a staple of the geochemical community. But yeah, that was what got me into more of the chemistry side of things, was getting involved with climate studies, and then I was able to kind of find my way back to thinking about fossils like the Megalodon and dinosaur bones and things like that.
Awesome. Here's a good question. This is from Bailey. What is your favorite modern shark?
Well, my favorite modern shark is the thresher shark. When I was a kid, I had like a little thresher shark toy, and I just thought it was so cool that it has that long, imposing kind of looking tail. But the sand tiger is also a cool looking shark. It's got those like kind of diabolical looking teeth.
Here's another good question. This is from Alexa, who is 7 years old. Why are megalodon teeth chipped? And so I wonder if she's talking about the serrations on the side.
Yeah, if you're talking about the serrations, you can just imagine the predatory teeth. That's kind of a common thing. They basically just act like steak knives for chomping into things. I think I've seen folks talking about, like the predatory habits of Megalodon just involve literally taking chunks out of the whales that they preyed on. So having those little serrations in the teeth, it's the same thing that we see in like theropod dinosaurs. Like if you've ever seen like a T-Rex tooth, it's like a giant. That's a thing that they use to help them to carve through their prey.
Cool. Somebody said, Valeria said, threshers are the best. They are so cute.
I agree.
And also, this is just a compliment I want to pass on. Jim said, well done explaining those concepts. This is the most I've ever understood anything chemistry related in a long time.
Oh, thank you so much.
Good job, Randy.
Chemistry was really hard for me when I was in college. I probably had to take chemistry twice, so it's really cool to be able to see it applied to paleontology, where it's something that I I guess, understand better and find the connections there. So it's
Yeah.
like
Um,
it's really awesome to see those things working together.
yeah, having the application, like knowing how you would apply it, which has always been helpful for me with some, like, especially with math concepts, is as long as I know how I can apply that concept, then it's not so hard understanding it. But otherwise, it can be quite difficult.
Yeah, I had like a kind of a epiphany when I came to the conclusion when like talking about the section where I was explaining like the calibration of the quantisotope analyses to growth temperatures, where like you do that. It is the actual process of doing that is a little bit more involved, but it's at its foundation is just doing that, where you perform a linear regression between points to make that equation. And when I really started to understand that, I was like, oh, this is just y equals mx plus b. I remember doing this in high school, and I had like this kind of cool, like, oh, that's what we learned that for. Now I can learn about Megalodon, so it was all worth it in the end.
Here's another question. Doug asks, if Megalodon can maintain such high body temperatures, why couldn't they follow whales into colder waters?
That is a great question, and that is something that yeah, that we'll definitely want to think about. I think as I tried to kind of allude to was that yeah, that may not have been a contributing factor. It was likely more complicated than that. So it could have potentially been able to follow whales into these colder temperatures, but there could have been these other things going on, like increased competition with other predators that were doing really well. So yeah, basically, it's potentially more of a complicated scenario than what we may have originally thought in terms of it depending on this inability for the megalodon to go into these colder temperatures. And that's just part of better understanding whether it was in fact that it could maintain these high body temperatures.
And then Jack has a question. Do you think understanding megalodon physiology via isotopes will help narrow down its phylogeny?
That is also a really good question, because that was something that I didn't want to bring up, was that the phylogeny starts to get kind of sticky. I think it was just recently moved from, oh, I can't remember the name. Yeah, like the genus Otodontidae was just like kind of shifted around relatively recently, and I think that it could potentially, getting a better understanding of its physiology could help us to relate it to extant sharks like the white shark, and having a better understanding of how it lives, I think would be able to help us better understand where it fits in a phylogenetic tree.
Nice.
All right, that looks like so far, if nobody has any other questions, that looks like all the questions we have in either of our chats.
I have another question. Do you want to keep working on sharks in the future, or is there something else you want to work on down the line?
So before things started really ramping up with the quarantine, we're actually planning in my lab of working on a new batch of sauropod teeth. Actually, these little dinosaurs called Europasaurus. I think they've been referred to as like pygmy dinosaurs. So you can imagine kind of like the classic long-necked dinosaur, but they were just smaller, which to me just sounds adorable. And we have a bunch of little tiny pygmy Europasaurus teeth in my lab, and yeah, really getting excited to potentially work on those in the future. Anytime I can get back to working with dinosaurs, that's where I want to be. But any kind of vertebrate paleontology is I think where I want to be with my research.
And this is from Valeria again, and this is in relation to the question you answered regarding whether or not Megalodon could follow whales into colder water. She said lack of blubber, maybe higher metabolism that didn't work out well in colder water. Would this be a factor, or does this sort of stuff not really apply to sharks?
Yeah, again, that's a really good question, and I don't know if it's one that I have a really great answer for. I think it would also really depend on how how the megalodon actually maintain this body temperature. So like with white sharks, they have like this thing where they maintain their body temperature relative to the surrounding water by like storing heat in like this specific kind of muscle, like they're referring to as like regional endotherms. So something like that, as opposed to like a specific organ that was functioning as a means of maintaining body temperature. There's just a lot about that I probably couldn't give you a super sufficient answer to that, unfortunately. But that's about the best I can do in terms of estimating something. So I'm sorry for there not being more of a thorough answer, but yeah,
Yeah, that's what more research is for, right?
That's the
yeah,
best part of paleontology. There's always new questions to ask.
There's always things you don't know.
So earlier you were saying, Randy, that in your talk you went to community college first. Is it right?
hmm
Do you think that like really helped you later in your career? I mean, like, because for both Brittany and I, we have a little bit different paths in the paleontology. I didn't actually start in paleontology. I was a pre med, and then I didn't get into paleontology until I was a master's student. And Brittany, you started as
I
journalism.
have my undergrad is an English degree, so I definitely did not start out in paleontology. My master's degree right now that I am currently in, I am working for paleontology to go towards paleontology. But yeah, prior to my job at the Western Science Center, I was in humanities.
interesting. That's really cool. Um, yeah, so to answer your question, Gabe, yeah, I would say that yeah, definitely. When yeah, I kind of alluded to like some of the things that I was interested in. Like when I first started at community college, I wanted to be like a sound engineer. I was taking classes to learn how to be like a recording engineer, and then I was set on trying to do marine biology for a while. I thought that was what I wanted to do. So ironically, I found my way back to sharks here in kind of in a different way. Um, and then I think I ended up I had always been interested in geology. Like I said, like as a kid, um, I went to like the LA Museum of Natural History a lot with like my mom and my older brother, and that really helped for that passion to grow as a kid. But I never thought about it as something that I would do like academically until I got to community college, where I had a couple of really great professors, Brian Wilbur and Martha House at Pasadena City College, who really encouraged me to actually pursue that interest. And yeah, like I said, I got involved in things like field work that I thought was just awesome, was just like getting to go camp and collect samples and live in the wilderness for a few weeks at a time. Um, and so, yeah, absolutely, my experience at PCC guided me towards geology, which ultimately led me into geochemistry, where I am now.
That's awesome.
It was that first geology class. Get some.
Yeah, yeah, it was funny because I was like trying to just complete my you complete for I don't know if I'm not even sure if it's still like this. You complete something called the I get C, which is like a form of like all the classes you need to check off to transfer. Um, and I thought that I was almost done because I was doing like the bare minimum, and I was like, oh, I'm gonna get out of here and be done. And then I took my geology class, and I was talking to my professor, and he's like, oh, well, you need to take math and chemistry, and I was like, all right, I'll be here for a few more years. And I just took as I was finishing my math and chemistry and all my other requirements, I just took like all of the geology classes that they offered there. So it ended up working out in the long
Nice. I had to do something like that too, because like I wanted to originally take a minor in archaeology, and then
run.
I was doing it, and all of a sudden my program was like, "No, sorry, you can't do a minor." So I was like, "Okay, then I guess I'll just leave then. Bye."
I went to community college after I did my bachelor's because I realized I was like, wait, I want to go into this. I want to be a paleontologist, but I have like no science classes because I got an English degree. So I
Mm,
used community college classes, Mount San Jacinto College here in Hemet, to basically take all the geology, all the biology that I
mm.
had taken in undergrad, so that I had at least some foundation to take to a master's program and be like, hey, I swear I can get a decent grade in a science class. Let me be a
That's
science.
really cool.
Yeah, so I've personally found community college to be a really important step in my career,
Mm,
um, that otherwise I probably wouldn't have been have. And it's a lot cheaper
yeah.
than taking those classes at a university.
Mm.
Oh yeah,
Um,
definitely.
yeah, that's interesting that I say that because I was actually also thinking about doing that because yeah, like I just got my degree in geology and I was actually thinking about that afterwards. It's like I wonder if I could go back to PCC and take like all their biology classes and then yeah, basically the same thing as you, be able to build a case that I can be a paleontologist.
Yep.
So I'm gonna shift really quick because I've been wanting to talk about Star Wars for a second. So, as we know, in the world of Star Wars, a lot of the creatures were inspired by real animals and some paleontology, things like that. If you
Mm.
were a Jedi paleontologist or whatever, is there a specific animal you would like to try to study in the galaxy, Star Wars galaxy?
Gabe is bringing the hard-hitting questions this Fossil Friday.
Man, that's such a cool question. Okay, so let's see. If I were to try to do that, I'm thinking about kyber crystals being like a sort of almost semi-sentient object in that they're minerals, but then in a way they have like a spirit of their own in the way that they identify with a Jedi, and that's how you end up with your lightsaber color. So I would wonder if there was an animal that had like a symbiotic relationship with the kyber crystals, like a sort of like force sensitive animal. Like we've seen in Rebels, there's like the Loth wolves and things like that. These animals that we know have some force sensitivity. So like symbiotic relationships in nature are really interesting to me. And then maybe studying like how that evolved would be really cool.
Nice.
That's probably the most interesting topic that I could think of off the top of my head.
That would be cool. That would be really interesting for the Jedi archives too, probably.
Yeah, I think that was like a thing in Legends, right? There was like a science core basically in the Jedi Order where it's like if you didn't make to fully fledged Jedi, it's like okay, well you can go do other stuff.
That's probably where I would
Correct
end
me.
up, for sure.
Yeah, you know, it sounds because it sounds like the place to be if you ask me.
Yeah, I'd fail my
You don't have to.
Jedi. I'd fail my Jedi Knight test to go to the science core, probably.
Yeah, it's like science core or fight the Confederacy of Independent Systems and just have to destroy droids all day long. I think I'd probably choose the former rather than the latter.
Yeah. People are destroying droids, and I'm like in the Naboo Trench studying the Sando Aqua Monster or something.
All right.
There's always a bigger fish though. Don't forget.
Maybe as we get closer to May the 4th, we'll have to do a Star Wars Fossil Friday.
Oh, okay. No, that's happening now. You heard it here. We're gonna do a Star Wars.
I've given Gabe an idea. All right. Well, thank you so much, Randy, for sharing this with us today.
Well, thank you all so much for having me.
Yeah. And everyone, we will be having another Fossil Friday live web chat today at 3 p.m. Pacific time. Jeanette Perlow, who is a PhD student at University of Florida and the Florida Museum of Natural History, is going to talk to us about four-tusked elephant relatives, which I'm personally very excited about since we do a lot of proboscidean stuff at the Western Science Center. And if anybody would like to support our two museums as we continue to be closed through this lockdown, there will be information on that, how you can both support the Raymond M. Alf Museum and the Western Science Center. The Western Science Center is actually currently soliciting donations for plastic as we have repurposed our 3D printing lab to produce PPE for local healthcare providers. So if that's something that you're interested in, but we know these are hard times, please feel free to do so. And join us again at 3 p.m. Pacific time for another Fossil Friday web chat. We are looking forward to seeing you all then.
Thanks, Randy.
Thank you.
Thank you.